Section 8.5, Rationalizing Numerators and Denominators of Radical Expressions. In Math 116 Intermediate Algebra, we only have to cover rationalizing denominators, so we will not be doing rationalizing numerators. So a radical is in simplest form if the radical has been simplified as much as possible, meaning anything that can come out has come out, but also radicals are in simplest form when there are no radicals left in the denominator. So you got to be careful that you understand that if you had, say for instance, 2 over the square root of 3, that is not in simplest form. So you have to go farther. Well, how do we go farther when there's really nothing we can do with 2 over the square root of 3? Well, we're going to do something called to rationalize, okay? So to rationalize a denominator means to rewrite the expression so that the denominator only contains a rational number, no radical. So to rationalize, we have to multiply the numerator and the denominator by a radical, the same radical, so that the radical in the denominator will be eliminated. So we have to multiply top and bottom by some radical so that when we multiply the 2 in the denominator, it cancels out. So for example, when we look at 1 over the square root of 2, if this was the square root of 4, then the radical would be eliminated because we know what the square root of 4 is. So we would have to multiply the square root of 2 by the square root of 2 to get the square root of 4. But whatever we do to the bottom, we have to do to the top. Now don't just assume it's always the same number. That's what some students go ahead and start just trying to memorize. And then when things change, they don't understand. So you're not just multiplying by the same number every single time. You're trying to multiply by something that will give us the smallest perfect square under the radical. So 1 times the square root of 2 is the square root of 2 over the square root of 2 times the square root of 2 is the square root of 4. And the square root of 4 is 2. So when we rationalize, we multiply top and bottom by the same square root, again, because that's just a 1, right? Square root of 2 divided by square root of 2 is 1. We're just multiplying by an interesting kind of 1. And that will make us eliminate the radical in the denominator. So for number 2, we have the square root of 7 over the square root of 12. Let's go ahead and separate them. Can anything come out of the square root of 7? No. What about the square root of 12? Well, there's a couple different ways you can go from here. I would take stuff out. Well, the square root of 12 is really 4 times 3, and 4 has a nice square root of 2. So a 2 comes out, right? This is where we go into our prime factorizations. So a 2 comes out and a 3 is left. Now, we still have to rationalize. We're not allowed to have a radical left in the denominator. So what do we need to multiply by? Well, the first nice square that 3 can go into is 9. So if we multiply top and bottom by the square root of 3, we would get the square root of 9 under the radical. So on top, because they're both underneath the square root, we can multiply them. So we get the square root of 21. In the denominator, we have 2 times the square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 we know is 3, so we end up with the square root of 21 all over 6. Now another way to think about it, if you want to, is if you had the square root of 7 over the square root of 12, you would first ask yourself, what's the first square that 12 can go into? Well, it would be 36. And what would we have to multiply by? The square root of 3, because 12 times 3 is 36. On the top, the square root of 7 times the square root of 3 is the square root of 21. On bottom, the square root of 12 times the square root of 3 is the square root of 36. And the square root of 36 is just 6. So did we get the same answer? Yes. There's going to be a couple different ways to get to it. You decide which way you want to go. So on number 3, we have the 3 over the square root of 10 times x. Well, what's the first square that 10 can go into? It's 100. If you try and do the factor tree, 10 is 2 times 5. There's no pairs to take out. So we know and then we have to figure out what about our x. Well, x has a power 1. To come out, we need 2. So we need 1 more x underneath because x times x would be x squared, and that would give me a power of 2. So on top, this 3 is on the outside, and the square root of 10x is on the inside or underneath the square root, so we could just write them side by side. Don't multiply the 3 times the 10. In the denominator, we have 10 times 10, which is 100, and x times x is x squared. So on top, we get 3 square root of 10x. On bottom, the square root of 100 is 10, and we take power divided by index, and 2 divided by 2 is 1, so 1 comes out, x to the first comes out, so we have 3 square root of 10x all over 10x. If this was a 2 and this was a 10, you would be able to cancel because you had multiplication. So be careful that you still maybe possibly could simplify more. I'm going to circle number 4 for you to do, and you should end up with 3 square root of 2 over 4. See if you can get to that answer. Alright, so on number 5, we have it all underneath the same radical, so let's separate them. So we're going to separate them into the square root of 3m over the square root of 11n squared. So, can anything come out? Well, not in the top, but in the denominator we see that n squared, 2 divided by 2 is 1. So we could leave the numerator as is, take out the n from the denominator radical, and we still have the square root of 11. Now we still need to simplify because we're not allowed to have radicals left in the denominator. So we'll multiply top and bottom by some square root. Well, what's the first square that 11 can go into? Is 121. So we need to multiply top and bottom by the square root of 11. So we end up with the square root of 3 times 11 is 33m. Again, because they're both under the radical, so we can multiply them. And n times 11 times 11 is 121. And we know the square root of 121 is 11. So we get the square root of 33m over 11n. Now, here's where I want you to be careful. A lot of students, again, what they try and realize is, or they try and memorize, is they go, oh, all I got to do is multiply the same by the same thing, multiply by the same thing, multiply by the same radical. That is not true when you get into indexes that are bigger than a 2. So here your index is a 3. So now you're looking to find the first number that they can go into as a cube, right? So we have the cube root of 6 over 5. We're going to separate that into the cube root of 6 all over the cube root of 5. There's nothing you can take out, so now we need to rationalize because we have a radical left in the denominator. So we need to multiply top and bottom by some cubed root. Now, again, we're not going to just multiply by 5 because 5 times 5 is 25. There's not a nice cubed root of 25. So what's the first number that 5 can go into that's a nice cube? Well, it's 125. So I have to multiply top and bottom by 25, the cubed root of 25, because that'll give me a nice cubed root. So on top we get the cubed root of 6 times 25 is 150, all over the cubed root of 5 times 25 is 125. Now if you do the factor tree on the cubed root of 150, nothing can come out, but go ahead and try the factor tree if you'd like. So we get the cubed root of 150 all over the cubed root of 125 is 5. Because 5 times 5 times 5 is 125. So I would know your cubed roots up to 5 cubed. That's about, maybe on your homework you'll go a little bit higher. On the test you probably won't. So make sure you know your nice cubes. Alright, so I want us to really practice when we have an index that's not a 2. Because that's where students kind of get caught up because they're not really understanding how to rationalize. They just memorized on the square roots to multiply by the same radical, which is not true for indexes bigger than a 2. So on number 7 we have p over the cube root of q. So what do we need to do? Well, how many q's do we have? We have 1. So how many more do we need to multiply by? Well, if we have 1, then that means we need 3 total to have a cube. So we need to multiply the cube root of q squared, the cube root of q squared, because 1 plus 2 would give me 3, and then I'd be able to take it out. So on top we have p times the cube root of q squared all over the cube root of q to the 1 plus 2, which is 3. And then 3 divided by 3 is 1. So we end up with p cube root of q squared just all over q. Alright, so on number 8, we have 9 over the cube root of 9 times a. So we need to multiply by some cubed root that's going to get rid of my radical in the denominator. So what's the first nice cube that 9 can go into? Well, it's 27. And so 9 times 3 is 27. We have a to the first power. We need 3. So we need a squared to make a total of 3. And whatever we do to the bottom, we have to do the same thing to the top. Again, it's like multiplying by an interesting kind of 1. So now we have 9 cubed root of 3a squared all over the cubed root of 9 times 3 is 27. A to the first time a squared is a to the third. So you end up with 9 cubed root of 3a squared over the cubed root of 27 is 3. And power divided by index as a to the first comes out. Now are we done? No. One more thing we can do. We can say 9 can be divided by 3 because it's all multiplication. So 3 can go into 9 3 times, and our final answer is 3 cubed root of 3a squared all over a. Takes a little bit more work to rationalize than a 2. So I'm going to circle number 9. I want to see if you can work it out yourself, and you're going to get the 4th root of 5y over y. See if you can figure out how to get to that answer. If not, let me know. So when we were looking at our denominators, we only had one radical, one radical, one radical. We didn't have a radical plus a number or anything like that. But in this next few problems, we're going to have, in a sense, a binomial in the denominator. So if the denominator fraction contains a sum or difference, you rationalize the denominator by multiplying by the conjugate. Now the conjugate just means to change the sign in between the sum or difference. So for example, if we have 3 over the square root of 5 plus 2, we're going to multiply the top and bottom by the square root of 5 minus 2. So we have 3 over the square root of 5 plus 2. When we're trying to rationalize with a sum or difference, a two-term, a binomial, we want to multiply by the conjugate, which is the square root of 5 minus 2 on top and bottom. Now why do we do that? Because of the fact that when we multiply a binomial times its conjugate, the outer and the inner will always cancel. So let's go and do our distributing. 3 times the square root of 5 is 3 square root of 5. 3 times negative 2 is negative 6. Now in the denominator, the square root of 5 times the square root of 5 is the square root of 25. Square root of 5 times negative 2 is negative 2 square root of 5. Inner gives me positive 2 square root of 5. And last gives me a negative 4. So do you see that the outer and inner are always going to cancel? And what happens is we know what the square root of 25 is. The square root of 25 is 5. So we get 3 square root of 5 minus 6 all over 5 minus 4. So we get 3 square root of 5 minus 6 over 1. Don't leave the 1 down there. We are understood to know that the 1 is there. So we don't need the 1. So 3 square root of 5 minus 6. So when you have a binomial in the denominator, multiply by the conjugate. So on number 11, we have 4 over 3 minus the square root of 5. So what do we need to multiply by? Well, we need to multiply by 3 plus the square root of 5. And whatever we do to the bottom, we do to the top. So I'll give you 12. 4 times the square root of 5 is 4 square root of 5. In the denominator, 3 times 3 is 9. I'm not going to show outer and inner because outer and inner will just cancel out. And negative square root of 5 times positive square root of 5 is negative square root of 25. So again, outer and inner will cancel because they are conjugates. So we have 12 plus 4 square root of 5 all over 9 minus the square root of 25 is 5. So now we have 12 plus 4 square root of 5 all over 9 minus 5 is 4. Now here's where students make mistakes because they're not sure how to cancel. So what I tell students to do is factor out what's in common with the top to see if you can cancel in the denominator. A 12 and a 4, there's a 4 in common, so I'm going to factor out a 4. And I'll be left with 3 plus the square root of 5. Now the 4's can cancel because they have multiplication, and I'm left with 3 plus the square root of 5. Some students try to do this problem by just taking the 12 divided by 4 and they get 3, but they forget that the 4 has to be divided by 4 also. So I suggest factoring it out so you don't make that mistake. Alright, so I'm going to circle number 12 for you to do. I'll give you the answer. The answer is 4x minus 4 square root of x all over x minus 1. Another way to write that would be 4 parentheses x minus the square root of x all over x minus 1. So either of those answers would be sufficient. Either of those answers would be sufficient, so make sure you can get to one of those answers. Alright, lastly, number 13, we have 4 square root of 3 all over the square root of 7 plus the square root of 2. So we need to multiply by the conjugate, which is the square root of 7 minus the square root of 2. And whatever we do to the bottom, we do to the top. So 4 square root of 3 times the square root of 7 would be 4 square root of 21. Then we get minus 8 square root of 6. We have, minus 4 square root of 6. The 4 stays on the outside, and 3 times 2 is 6. In the denominator, square root of 7 times square root of 7 is the square root of 49. I'm not going to show outer and inner because outer and inner will just cancel. And the square root of 2 times the negative square root of 2 is minus square root of 4. So then on top we have 4 square root of 21 minus 4 square root of 6 all over square root of 49 is 7, square root of 4 is 2. So we end up with 4 square root of 21 minus 4 square root of 6 all over 7 minus 2 is 5. Now, when you look at this, 21 is 3 times 7, so nothing comes out. 6 is 2 times 3, nothing comes out. So you may leave it in this form, or you can factor out the 4, and you get the square root of 21 minus the square root of 6 all over 5. So either of those answers would be sufficient.